Hi everyone. I wanted to do a quick follow-up to a previous video that I did. That video was called Can Rust Save the Planet? And I'm titling this one, a little bit tongue-in-cheek, Can ARM Save the Planet? Spoiler alert, it can certainly help. So, in this previous episode, I was comparing Rust to Node. And the primary focus of that video was looking at the energy usages of these two programming languages in terms of a web server and the web server doing various things. The most important test that I did in that video was for a REST application where I got some information out of a Postgres database and I returned it to a user as JSON information. So pretty simple test, but it was kind of more the real world test of the few tests that I did in that video. Go take a look at that video. There's more things in it. I'm kind of giving you the highlights right now. So in that specific test, the results were pretty underwhelming for Rust. If I remember correctly, there was around a 10% energy savings. If you took the Node application and you switched it to Rust, you got about a 10% energy savings, which, you know, we wish there was more. The planet needs more. One of the things that I said in that video was that I didn't have an ARM board to play with. So my tests there were all done on an an x86 Skylake NUC. And that is a 7-year-old computer, 14 nanometer processor. Anyways, I have a new toy. I got myself a NanoPi R6S. And let me show it to you. A little bit of show and tell going on here. This is the thing I got from a company called FriendlyElec. It's pretty well made. The case is well made. The device seems pretty good. It's got two USBs in the front here. One's a USB 3, one's a USB 2. It's got some LED lightings that do stuff that I don't pay attention to. It's got a nice case. The case acts as a bit of a heat sink. It's got space for an SD card, and it's also got an eMMC card that is part of the board. And the real reason why I wanted this was because it has 3 Ethernet ports, meaning that in the future I can turn this into a little router and do things with routers. Right now it is running Ubuntu 2204, but with a 5.10 kernel. So yeah, it's a nice piece of kit. It is based on the RK3588S processor, which is a Samsung 8 nanometer lithography. So it's about like half a year to 1 year old. I'm not quite sure, but it's pretty new. It's got 8 gigabytes of 2133 megahertz LPDDR4 RAM. It's got 4 high performance cores and 4 energy efficient cores. So yeah, in the previous video, I was given some suggestions in the comments about how I can improve the Node.js application, because I'm not a Node guy. I'm not a JavaScript guy. So yeah, there was some really helpful tips here. One of them was to use the web framework Fastify rather than the Express.js that I was using. And that gave a very significant gain. And the other gain that I got was from using node workers rather than having an Nginx do load balancing on 8 different applications that I was running. And that also was a pretty significant gain. It was so significant, these changes were so significant that for large data sets, the Node.js application was actually outperforming the Rust application. So I said, oh no. Not only was it outperforming Rust, but it was so fast that the bottleneck was no longer in the application I was running. The bottleneck noticed when I was doing the JavaScript code was actually I was maximizing the network card on the NUC. So it's like I'm not even getting the full performance out of Node because my network card is, well, my network card and my whole LAN local area network in my house it's at 1 GB. So I was maximizing that out, and I was just not seeing like how fast Node really was here. So anyways, my first concern was why is my Rust code performing so poorly against this Node.js code? Isn't Rust supposed to be a top tier performance language? So I optimized and I optimized and I optimized. And the optimizations that I was doing was focused on serialization. And eventually I gave up on optimizing it and moved the serialization into JSON into Postgres and got Postgres to do that serialization for me. And finally, I was able to get the Rust code to outperform the Node code, but this is kind of a mass solution. First of all, the text, the JSON formatted text that Postgres gives you using a function called JSON_AGG. It has new lines on every row. So that means that not only is there a new line, but there's a new line space. So that means that there is 2 bytes of data extra for every row, which means that if I have 2,500 entries in my database, I'm adding 5,000 more bytes. I'm adding 5 kilobytes of data to every response. And when you start to maximize your network card for this, that 5 kilobytes it's a performance hindrance because you simply can't shove out the bits that you want to shove out. So it becomes a performance hindrance in that case when you have big amounts of data. Not only that, but the result that you get is, it's text. So if you want to use it for anything else, if you want to use that data for anything else, such as generating an HTML page instead of generating a JSON return, well, then you've got to like reparse it and do all this work to get the information out. And it's just not a good solution if you want something generic. Not only that, but this JSON AG function inside of Postgres was actually a performance hindrance to Node. It wasn't all that much of a performance hindrance, like 2%, but it was there. It was real and it was measurable. So yeah, this JSON AG got my Rust code outperforming the Node, but it was just not a good solution. So I started looking over the web to kind of figure out what's going on. Why is my Rust code slow? And it turns out that the database driver that I use, which is called SQLX, is actually a pretty slow database driver for Rust. SQLX is one of the slowest Rust database drivers, but it does some really nice things for you if you use it properly. What SQLX can do for you is at compile time, it can check your SQL queries to make sure that they are valid before you even like your Rust analyzer can tell you, no, your query is bad, you need to fix this, even before you type cargo build. So yeah, SQLX has some really good parts to it, but the performance is really bad, especially when you start getting up into the higher amounts of rows returned from the database. So I switched to Tokyo Postgres as my database driver, and I saw some really, really big gains from moving to Tokyo Postgres. So let me show you some code to see kind of what I did between the last video and this video. So on the left here, we've got the Node code, and on the right, we have my Rust code, and I'll highlight some of the Rust code changes first. So first of all, I'm using BB8 which is a database pool that you can hook in your Tokyo Postgres into. And a database pool is so that databases can have problems if you keep establishing new connections every time you want to use the database. So what a database pool is, it sets aside a whole bunch of connections right at the start, and it allows you to reuse those connections as needed in an asynchronous way. So yeah, it's just a nice way of not like reestablishing connections over and over and over onto the database. So that's what this code, all this code does. It just kind of sets up that pool of database connections that can be used later. And then I pass in that pool of database connections into my Axum web framework here, using with state. And this is very similar to how I was doing things with SQLX. And let's jump into the actual handlers for my GET requests. So in here, what I'm doing is I'm getting that connection pool, and I'm getting an individual client connection from that pool here on line 81. I am then doing the SQL query using this macro, and it's very simple. Select star from users. So there's nothing special going on here. It's just a simple query, and that will return to me a vector of Tokyo Postgres rows. So I'm taking those rows and I'm feeding it into a helper function called getResp.json. So get the JSON response. What I'm doing in here is I am allocating some space for a vector of U8s, and I am then getting the users. So what do I mean by I'm getting the users from these database rows? And while I'm at it, let's do some fix-ups here. Let's call this rows, and we'll pass in rows. So I'm getting the users from these rows. And what do I mean by getting the users? Well, I have a simple loop to call a user function, which is an impl on those Tokyo Postgres rows. And what it does is it just gets each column from the database, and it sets it to items in a user struct. So the user struct is a little bit interesting in that it is just the identifier, which is an I32, which is fine to do a dumb copy of. I32s are cheap. But the other two, the first name and the last name from the database, is just references to information in that row. So let me actually show you. Let me actually show you the database table. So it's very simple. It's just a UID, F name, last name, and all the first names are called first underscore name, and all the last names are last underscore name. So yeah, it's simply taking those rows and taking string references so that I'm not doing like a string allocation for each first name and last name. I've just got a reference into the row. So I'm not doing mem copies because of that. I'm not doing memory allocations because of that. Other than I have these user kind of aliases in the stack. So yeah, I'm going through that and I'm making a vector of these users. And then I take this vector of users and I use a technique from the Tech Empower. So Tech Empower is a website that does a lot of web framework performance benchmarking. And one of the techniques that they have is this writer technique where they're using JSON Serde 2 writer to write in to serialize and quickly fill up their response buffer with the serialized data. So what happens here is that Serde JSON provides a to writer function, And that toWriter function is going to create a JSON Serde, a Serde JSON serializer using the writer that we are going to provide. And then it serializes that slice. I turn my vector into a slice, and it serializes that slice of users, which means that you get the nice kind of array format of you've got the open square, and then you have each row of the database as JSON, and then you have the square brace closing it so that it's an array of JSON data. So it does that all nicely for you. You just kind of have to shove it into the writer here. So what is Tech Empower specifically doing? Well, it's being a pretty dumb pipe. So the Tech Empower writer is receiving a slice of bytes, which is the data that has been serialized using JSON Serde, and it's just shoving data using the bytes crate, byte mute, a buff mute using the bytes crate, and it's just kind of dumb shoving bytes into the provided area where data can be collected, which is this response. So I know I was explaining that a little bit complexly, but it's actually rather simple. You just kind of have an area where data can be shoved into. You serialize data and then get the tech empowered writer to just dumb shove bytes into that area that you've allocated. So now we've got this serialized JSON array in this response, and if everything went well, we just return that to the user. So it's as simple as that. I've also done a manual conversion. Instead of using JSON Serde, I did manual JSON creation. And that's just kind of writing this data into a string using the write call. This doesn't give any performance benefit whatsoever. JSON Serde is just as fast as doing it manually, sometimes even a little bit faster. So yeah, that's the Rust code. Those are the changes to the Rust code. What about the Node.js code? Well, the Node.js code was extremely simple to update. So first of all, instead of using Express.js, I use this Fastify plugin. And Fastify is, as far as I was able to tell, it's a one-to-one replacement for Express.js, meaning that I did not need to do any changes to my handlers for the web requests. Nothing at all changed here. I just changed the name from Express.js to Fastify. I made sure that I was using a connection pool. I'm not sure if I was using that before. I think I was. So that isn't even a change. I just started using Fastify and blam, got extra performance. And the other thing I did was that I used worker node workers instead of using an Nginx to load balance from clients. I got Node to spin up 8 different node processes and using this cluster stuff. Right here, using cluster. And that was an immediate performance improvement as well. So yeah, these changes to Node were so good that I started maximizing out my network card rather than being able to see how fast Node was. However, before I changed to Tokyo Postgres, I was not maxing out my network card, and I had to do like different stuff to try and figure stuff out. And eventually, like, I got nowhere until I used this. I used this JSON ag thing here, and yeah, that wasn't a very good thing for me. It wasn't a very good solution to the problem I was having. But it did get me faster. So, yeah, let's take a look at the numbers. So here are my numbers for different sizes on the x86 machine, and I also tested this on my nice new toy to see how it's going. And you know, we're about to see some major differences between ARM and this x86 going on. So I measured at 3 different levels here. I measured where my database size was 25 rows deep, 250 rows deep, and 2,500 rows deep. And what you can see is at 25 rows deep, Node.js is less performant than even the SQLX going on. However, the Tokyo Postgres was extremely quick at this. And it's also important to look at the amount of electricity used to see how many requests that we get per milliwatt of electricity. So with Node, I was able to get 0.3 requests per milliwatt of electricity. And using the best techniques with Rust, I was able to get more than half of a request with 1 milliwatt of electricity. When I turn this up to 250, now you can see that the SQLX is performing worse than the Node solution. So with SQLX here and with Node, we're not quite hitting at this level, maximizing the network card, but Node is getting very close. With Tokyo Postgres, I am maximizing, and with JSON AG, I am also maximizing. Now you might be thinking right now, why is there a difference between the amount of requests per second? Why is there such a difference in requests per second when you're maximizing the network card? And that's because there's an extra new line and an extra space, which takes up extra room in the packets that I'm sending, meaning that there's just more data to send on the network card, meaning that things are going to slow down because I've only got so much space on that network card. So yeah, as you can see, the Rust Tokyo Postgres is very fast here. And we're getting at this level with 250 rows, we're getting 0.17 requests per milliwatt of electricity, and the Node code is getting 0.1 requests per milliwatt of electricity. And the SQLX with normal JSON is only getting 0.09. And the results for 2500 are very similar, except now Node has maximized the network card. But still, SQLX with Rust did not maximize that network card. So yeah, the performance, as you can see, the SQLX electricity usage is still worse than the Node code. Can't do that. But we're still outperforming using JSON AG and Tokyo Postgres. So let's look at the ARM numbers, and this is kind of the oh my god moment. So with 25 rows, even though we're not able to do as many requests per second on this little NanoPi R6S, our energy usage is much, much better. So the best energy usage that I was able to get on this little ARM machine was 3.2 requests per milliwatt of electricity. So that's nearly 6 times better than the x86 equivalent, and more than 10 times better than Node running on the x86 equivalent. So that's an oh my god moment. Imagine if in all of the data centers that Amazon, that Google, that Microsoft is using, imagine they replace their x86 machines with ARM machines. they might be able to get, you know, four times the electricity savings using this. Not only that, but they don't have to cool this because there simply isn't that much electricity being generated here. So yeah, they can. This is a real area where savings in electricity, so you don't have to generate as much carbon to create this electricity. You don't have to spend as much resources cooling things to use this electricity. There's some real savings here, not only to like the carbon footprint of these big companies, but just the amount of money they can save. Their electricity bills are very large. So like a 4 to 5 times savings is huge for them. And as we keep getting up in the amount of rows, the amount of difference between these things starts getting more and more extreme. So with 250 rows, our best case with Rust is 1.31 requests per milliwatt of electricity, while x86 could only do 0.17. So we're getting close to, let's do some math here with the calculator. So 1.31 divided by 0.17, 7.7. So that's 7.7 times better electricity savings. And versus the node, like, this is huge. 13.1 times better than the x86 node running if we ran Rust on ARM. Now, of course, we do start running into the network being maximized case for 2500. So these two aren't really good measurements to look at right now, because the network card is being maximized. But yeah, like even node versus node, that's some big numbers there. You know, that's 7 times better node versus node. That's 10 times better x86 ARM Rust versus ARM x86. So yeah, there's some really big improvements here. So yeah, let's go back to my original question. Can ARM save the planet? It can certainly help. So thank you very much for watching. I hope you've learned something about my new toy. I hope I had fun doing a show and tell, and that was the point of this. So yeah, thanks for watching, and I'll see you guys in the next video.